Welcome to the foundation of your journey toward becoming an Appian certified associate. In this chapter, we will establish the essential building blocks of low-code development and the architectural principles that define the Appian platform. This course is an unofficial, independently produced study guide. It is not affiliated with, endorsed by, or connected to Appian Corporation in any way. Appian and ACD101 are trademarks of their respective owners. This content is for educational purposes only and does not guarantee success on the official certification exam. If you are aiming to validate your skills professionally, this course is designed specifically to bridge the gap between abstract concepts and the practical, hands-on tasks required for the ACD101 examination. Achieving this certification demonstrates a command over the Appian Designer interface and provides a clear signal to employers that you understand how to build robust enterprise applications from the ground up. By following our structured curriculum, you will navigate the complexities of data modeling, process automation, and the SAIL interface framework with confidence. We focus on the core methodologies that turn a project requirement into a functional, scalable software solution. This is your opportunity to formalize your expertise and gain the credential necessary to lead modern automation initiatives. Transitioning into the specifics of the Appian platform, we must first recognize that the environment operates under a philosophy of simplicity through abstraction. The designer role is not merely a task of configuring components, it is an exercise in architectural thinking where you decide how data, logic, and user interfaces interplay within a unified application container. We will spend our time looking at the Appian Lifecycle Management Framework, which organizes development from the inception of an object to its eventual deployment in a production environment. Understanding the hierarchy of these objects is crucial because it dictates how security is applied and how components are referenced across the platform. When you organize your site navigation and data structures effectively, you minimize technical debt and significantly improve the maintainability of your enterprise solutions. The core development experience is driven by the design, build, optimize methodology, which requires a disciplined approach to every feature you implement. You will learn that navigation within the Appian Designer is designed to keep you focused on the business problem rather than the underlying infrastructure. By leveraging the cloud-based nature of the platform, you gain access to powerful tools, but this also places the responsibility on you to ensure that your configurations remain performant and secure. We will examine how the Appian community and standard documentation serve as your primary toolkit during the development process. As you progress, you will see that every object you create exists within a context that requires thoughtful consideration of the overall application architecture. Getting comfortable with the developer ecosystem is the final piece of this introductory puzzle, as certification is fundamentally about adhering to best practices in a real-world scenario. The path to ACD 101 is not just about memorizing terminology, but about developing an intuitive grasp of how the Appian platform handles data persistence and workflow orchestration. We move beyond simple configuration to understand why certain patterns are preferred over others in enterprise automation. By mastering the structural hierarchy and the operational requirements of the designer interface, you set yourself up for long-term consistency in your projects. We are setting the stage for everything that follows, ensuring that your foundation is solid before we dive into the specific complexities of data modeling and interface design. I look forward to our next session together. Welcome to our deep dive into the foundational data structures of the Appian platform. In this chapter, we will master the transition from relational database concepts to the Appian native representation of your business information. Custom data types, or CDTs, serve as the primary mechanism for modeling structured data within Appian. While you might be accustomed to defining tables directly in a relational database, Appian prefers a structured approach where the schema is defined via XML schema definition files. The XSD file acts as the blueprint for your data, dictating the structure, data types, and primary keys before the database even sees the table. When you create these structures, you are essentially defining a contract between your business logic and the underlying storage layer. Ensuring that every field has a clear purpose and an appropriate mapping is critical for downstream stability. If your XSD defines a field as an integer, Appian will rigorously enforce that expectation throughout the application. Neglecting these strict definitions often leads to subtle errors that only manifest once user data starts flowing through the system. The bridge between these logical definitions and physical storage is the data store. Think of the data store as the configuration layer that maps your CDTs to specific database tables and handles the complexities of persistence. Within this object, you define the entity mapping, which links your custom XSD structure to a physical database table name. Crucially, this is where you enable auto-generation for primary keys, ensuring that every record receives a unique identifier without manual intervention. You should always ensure that your primary key is clearly marked with the appropriate tags in your XSD, or the data store will struggle to identify it as the identity column. A misconfigured data store might fail to update the schema automatically, leaving your application unable to persist data even if the logic appears sound. Maintaining consistency between your XSD fields and the data store entity configuration prevents the dreaded schema mismatch errors that often plague early development. When designing your data, you must adopt a naming convention that remains consistent regardless of the underlying database vendor. Whether you choose to map to an existing table or allow Appian to generate new ones, the alignment between your data types and the relational schema remains paramount. For example, using a text type in Appian for a field that captures a large, unstructured blob is an inefficient use of resources and may cause truncation errors at the database level. Proper data alignment also impacts indexing, which is vital for the performance of your record types later on. Avoid the temptation to build overly complex or nested CDTs, as these can quickly become difficult to maintain and query. Instead, lean toward flatter, more manageable structures that represent discrete business entities. This simplicity ensures that your data layer remains agile as your business requirements evolve over time. In the ecosystem of an Appian application, your CDTs and data stores are not merely static containers. They are the bedrock upon which all your processes and interfaces stand. By getting these right from the start, you provide a stable foundation for every object that follows, from your complex process models to your interactive sale forms. Take the time to validate your schemas early and verify your mappings during the initial design phase to save yourself from potential refactoring later. Data integrity is the silent guardian of your application's health, and it starts with the careful architecture of these fundamental data objects. By adhering to these practices, you ensure that your data is both reachable and reliable. As you build, remember that every field addition carries a long-term cost, so be deliberate about every piece of information you model. See you in the next lesson. Welcome back. In this chapter, we are going to master the core of Appian Data Fabric by diving deep into the configuration and design of record types. Record types function as the foundational abstraction layer in Appian, moving beyond simple database table representations to create a unified view of your business data. When you initiate the creation of a record type, you are essentially defining a semantic model that sits on top of your underlying data source, whether that is a cloud database table, a web service, or an integration. The designer interface provides a structured environment where you map these data sources, ensuring that the platform understands the structure and relationships of your information before any user interface components are built. Selecting the correct data source is the most critical first step, as it dictates how data will be retrieved and whether it can be synchronized for performance. By defining these structures correctly at the start, you avoid unnecessary complexity later in the development lifecycle when building views or complex queries. Once the data source is established, the focus naturally shifts to how that information is exposed and consumed by end users through the record list and the record header. The record list serves as the primary gateway for users to interact with a collection of objects, requiring thoughtful configuration of columns, sorting, and user-friendly display labels. Within the record type designer, you gain the ability to define the header, which acts as the visual anchor for a specific record instance and provides immediate context, such as the record status or its primary identifier. Configuring these elements effectively transforms raw data into an intuitive interface where users can easily distinguish between individual entities. When you prioritize clear headers and organized lists, you reduce the cognitive load on your users and improve the overall accessibility of the application data. The true power of this architecture becomes evident when you implement record views. which allow you to display specific subsets of data or related information tailored to different user roles or task requirements. Each view is an opportunity to curate an experience that emphasizes relevant details, such as showing financial history to a manager while hiding it from a general staff member. By utilizing the record interface, you keep the presentation logic separate from the data definition, which makes maintenance significantly easier as requirements evolve over time. You should treat the record as the central hub of your application, ensuring that all related process actions and dashboards can easily reference it without redundant data fetching logic. This centralized approach not only streamlines development, but also ensures that the data presented remains consistent across the entire platform. As you build these types, keep in mind that the user experience hinges on how effectively you leverage the inherent features of the data fabric to visualize information. Reporting capabilities are greatly enhanced when you provide users with robust filtering and sorting options directly within the record type configuration. While you might be tempted to build custom interfaces for every requirement, using the native record infrastructure often provides better performance out of the box, because Appian is optimized to handle these requests efficiently. Always strive to balance the richness of the data presented with the clarity of the interface design, so that developers on your team can easily support the application in the future. Focusing on these foundational aspects during the initial setup will provide a scalable and maintainable data strategy as your application grows in size and complexity. I will see you in the next analysis. Welcome back. In this lecture, we are going to explore how Appian Data Sync transforms record performance and how to effectively configure relationships between your records. When we talk about data sync in Appian, we are essentially talking about a fundamental shift in how the platform interacts with its underlying data sources. Historically, Appian relied on direct queries to external databases, which meant every interface request had to wait for the database layer to process that request before displaying information to the user. By enabling data sync on a record type, you allow Appian to maintain a local, high-performance cache of that data within the Appian data fabric. This mechanism drastically reduces the latency associated with remote database calls because the execution engine queries the synced cache instead of the external source. You will find that pages load significantly faster, and the overall responsiveness of your application feels much more fluid for the end user. This is not just a performance gain. It is a way to shift the burden of execution away from your database transactions. To enable and maintain this sync, you need to be aware of the source changes and potential synchronization errors. When you toggle the sync feature on a record type, Appian begins to track the data from your source, whether that is a relational database table or a web service, and updates its internal representation automatically. However, schema changes at the source, such as renaming columns or changing data types, can trigger synchronization errors that you must address to keep the data fresh. If the sync fails, you are provided with logs that help identify exactly where the ingestion process encountered a conflict. It is your responsibility as a developer to monitor these health checks, especially after structural changes are applied to the external schema. By handling these alerts promptly, you ensure that the data fabric remains a reliable single source of truth for your SAIL interfaces. Beyond simple caching, the true versatility of synced record types comes from their ability to define relationships between different entities. Configuring relationships requires you to map fields from one record type to another, effectively creating foreign key-like associations within the Appian layer. Whether you are dealing with a one-to-one mapping, a one-to-many relationship, or a many-to-one structure, the configuration follows a consistent pattern that allows you to join data seamlessly. For example, if you have a record for employees and a record for departments, creating a many-to-one relationship allows you to pull department details directly into your employee record views without needing complex queries. You simply define the common field, specify the cardinality, and the data fabric handles the underlying complexity of the join. Primary advantage of these configurations is the simplification of your data modeling strategy. You are no longer required to write extensive query entities or complex custom data types to bring together related information from different sources. By leveraging these internal relationships, you treat your record types as the primary interface for your business objects, which keeps your logic clean and predictable. This modular approach lets you extend functionality without introducing tight coupling to the database schema, as the relationship logic lives within Appian. During the development process, you will notice that this methodology significantly reduces the lines of code you need to maintain in your expression rules for data retrieval. When you utilize the built-in relationship capabilities, you are effectively letting Appian manage the overhead of data discovery for you. There is a natural concern regarding data freshness when using synchronized data, but Appian manages this through efficient background refresh cycles. You can configure these refresh patterns or trigger them manually, ensuring that the cache stays sufficiently close to the state of the real-time database. Keep in mind that for read-heavy applications, the performance benefits of avoiding direct database hits almost always outweigh the minor trade-off of a slight delay in data propagation. When you architect your application with these synced relationships in mind, you are setting yourself up for long-term scalability. The platform is designed to handle this abstraction layer robustly, provided you adhere to the best practices of defining clear, unambiguous relationships between your record types. See you in the next lecture. Welcome back. In this chapter, we explore how to bridge the gap between static data and active business processes by implementing record actions. Record actions are the primary mechanism for enabling users to perform operations directly from the data layer in Appian. By configuring related actions and list actions, we stop treating data as a passive entity and instead transform it into an interactive platform for business logic. When a record type is synchronized, Appian provides a powerful automated action generator that saves significant configuration time. This tool automatically maps your record fields to process parameters, which is essential for maintaining consistency across your application. Instead of manually architecting every input, you rely on the platform to establish the initial structural link between the interface and the background process model. This foundational step is critical for moving from read-only data displays to fully functional, transactional workflows. The core of this interaction lies in the ability to pass context from the record view into the process model. When an action is triggered, Appian needs to know which specific data point the user is currently looking at to act upon it correctly. This is where the record type identifier, or RPID, comes into play as a crucial contextual variable. By utilizing this identifier, you ensure that the process model always targets the correct row in your database table. When you map this value to a process parameter, the process instance inherits the identity of the record, allowing for precise create, update, or delete operations on the individual data instance. Without this reference, the process would lose the specific context required to distinguish between different entities in your dataset. To implement a successful CRUD workflow, you must look closely at how the interface, the record, and the process model communicate. When a user initiates an action, such as updating a customer record, the process model should be configured to accept the record data as an input. You can leverage the record action configuration to pre-populate form fields, providing a seamless user experience that reduces the chance of manual data entry errors. The automated generator handles much of the plumbing, but you must remain vigilant about security and visibility settings applied to these actions. By controlling who can see and execute these actions, you maintain the integrity of your data fabric and ensure that users can only initiate workflows that are authorized for their specific role. The result is a coherent user journey where viewing data and modifying it feel like part of the same fluid interaction. Understanding these mechanics is essential for the exam, as it tests your ability to connect the dots between high-level record design and functional process execution. Think of the record type as the visual representation of your business intent, while the process model provides the logic to achieve that intent. By consistently utilizing best practices and mapping process parameters to record identifiers, you build predictable and maintainable applications. Always verify that your process security corresponds with the record action security, as these layers work in tandem to protect sensitive operations. Once you master the flow of data through these channels, you will be able to design robust interfaces that allow professional-grade interaction with complex underlying data architectures. I look forward to our next session together. Welcome back. Let us explore the intricacies of advanced record filtering to control how data is presented within your application. In this segment, we will distinguish between the mechanics of source-level security filters and the interactive options provided to the end user. When we talk about filtering data within an Appian record type, We must first address the distinction between static source filters and dynamic user filters. Source filters represent the initial layer of data reduction, often applied to ensure that the record list only contains rows that a user is permitted to see based on security attributes. These are configured directly within the record type object and serve as an immutable constraint on the underlying data source. Because source filters are evaluated at the query level, they are highly efficient and effectively reduce the dataset before it reaches the presentation layer. You might use these to limit records to only those owned by the current user or to exclude archived information. By strictly defining these boundary conditions, you ensure that even before a user interacts with the interface, the data governance rules are rigorously enforced. This separation of concerns is fundamental to building secure applications that scale well across enterprise environments. Beyond these architectural constraints, we want to provide the user with the ability to slice and dice the data dynamically through interface-level user filters. These filters are defined within the record's configuration and appear as interactive components, such as drop-down lists, date ranges, or checkboxes, alongside the record list grid. Unlike source filters, which are hidden from the user and act as hard constraints, user filters allow the operator to navigate large datasets by applying temporary contextual criteria. When you configure these, you map specific internal fields to the filter input, enabling the user to search by status, date created, or any other relevant dimension. It is important to note that these filters use expression power behind the scenes, which allows for complex logic, such as defaulting a filter value to the current date or filtering based on multiple related fields. This flexibility transforms the record list from a static table into a powerful, functional search tool. Performance is always a consideration when designing these filters, especially when you're dealing with large datasets or complex data relationships. Every time a user interacts with a filter, the system must reevaluate the record query, which can potentially introduce latency if not handled judiciously. Using indexed fields in your source data for these filter operations is a standard practice to keep responsiveness high. Additionally, you should be mindful of the number of active filters you expose to the user, as an overcluttered interface can lead to cognitive load and unnecessary query complexity. When you design your filters, try to anticipate the most common search patterns and optimize the configuration for those specific use cases. Keeping the filter logic streamlined within the expression editor will assist in maintaining a snappy user experience that feels like a native part of the platform. Finally, consider the nuances of expression-backed filters, which offer a higher degree of customization for dynamic data visibility. This approach allows you to write conditional logic that determines which records appear based on more than just fixed columns. By leveraging the full capabilities of the expression language, you can construct filters that respond to variables, user profiles, or even the current state of a process instance. This level of control is essential when the standard declarative options do not meet the specific business requirements of your application. While this complexity provides great power, it also requires diligent testing to ensure that your filter logic does not inadvertently hide data or cause unexpected results. Properly configured, these advanced techniques ensure that users find exactly what they need quickly, while the system remains performant and secure. See you in our next session. Welcome back. In this chapter, we will explore the mechanisms of database integration and querying to ensure you can interact with data sources beyond the standard record type paradigm. When we step outside the convenience of the record type ecosystem, we must interface directly with the underlying relational database management system using Appian's query framework. This is a fundamental skill for any developer, as business requirements often dictate that we interact with legacy tables or perform specific low-level data manipulations that fall outside the abstraction layer. To do this, we rely on the query entity function, which acts as the bridge between your expression-driven logic and the physical data store. The query itself is defined by a data query object, which serves as a structured map for the engine to translate your intent into valid SQL. By mastering this structure, we gain precise control over how data is retrieved, ensuring that our applications remain performant even when dealing with large datasets or complex join requirements in non-indexed tables. The data query object is essentially a configuration map that contains our primary instructions for the database engine. Central to this object is the entity parameter, where we specify the data store entity constant that points to our database table. Once the target is established, we must define the selection criteria using the selection parameter, which allows us to request specific fields rather than pulling an entire row of data. Selecting only the necessary columns is a critical performance practice, as it reduces the payload that must be serialized and transmitted to the application server. Furthermore, we must understand that querying is not just about retrieval, but about filtering, which we implement through the logical expression parameter. This parameter allows us to build complex criteria using logical operators, effectively narrowing down the result set to the specific records required for our business process. Filtering, while essential, is rarely sufficient on its own without a mechanism for ordering the returned dataset. We achieve this by using the sorting parameter, which accepts a sort info object that dictates the field to act as the pivot and the direction of the sort, either ascending or descending. When working with these queries, we must also be aware of the paging info object, which controls how much data is returned in a single batch. By setting a specific batch size, we protect the system from memory exhaustion issues that might otherwise arise from attempting to process massive result sets in one go. It is vital to view these parameters as constraints that govern the interaction between the Appian expression language and the database layer. Once we define these structures clearly, the Appian engine handles the translation to the appropriate database-specific SQL dialect, abstracting away the platform-specific syntax while maintaining the integrity of our query logic. Designing these queries requires a disciplined approach, especially when we consider that improper query structures can lead to increased latency and unnecessary server load. We should always aim to minimize the number of calls to the database by batching operations or utilizing the record data service whenever the use case permits such an approach. If we find ourselves writing complex queries that must be reused across multiple interfaces or processes, the best practice is to encapsulate this logic within a dedicated expression rule. This keeps our interface definitions clean and provides a single point of maintenance should the underlying schema change. By understanding the life cycle of a query from the initial expression rule call to the final execution at the database level, we can diagnose performance bottlenecks more effectively than by simply relying on trial and error. This structured interaction ensures that our integration patterns remain robust and, more importantly, predictable during the rigors of production use. In the next session, we will investigate the security implications of these data access patterns. I hope to see you then. Welcome back. In this lesson, we will focus on the mechanics of data security and access control within the Appian data fabric to ensure consistent protection of sensitive corporate information. When we approach the topic of security, it is helpful to think of it as a layered architecture rather than a single checkbox. In Appian, data-level security is governed by the specific configuration of your record types and the underlying data store entities. We must first understand the hierarchy of access where the security settings defined on individual objects propagate down to the data they expose. The Security tab of a record type acts as the gatekeeper for user interaction, determining who can view, edit, or manage the data records themselves. It is rarely sufficient to rely on basic visibility. Instead, we implement record-level security to filter rows based on user attributes or their specific business roles. By utilizing security rules, you effectively move away from a one-size-fits-all visibility model to a dynamic system that responds to the context of the logged-in user. This approach ensures that a sales manager only perceives the data relevant to their specific region, while an executive might maintain a wider lens across the entire organization. At the heart of this system lies the logic of allow versus deny, a fundamental concept in enterprise security, which often creates confusion if not handled with care. When multiple security rules are applied, it is vital to know that if any security rule denies access to an object, that denial effectively overrides any permissions granted by other rules. This inclusive approach to restrictive security means that we must be deliberate when crafting our security rules to avoid accidental lockouts. Within the record type, we configure security rules that evaluate Boolean expressions against user groups or user properties. These rules decide whether a user can interact with the record, update its values, or view the data entirely. If you have a system where temporary contractors only require read-only access while permanent employees require editing capabilities, you should define separate security groups and assign them explicit permissions. By keeping these groupings clean and granular, you simplify long-term maintenance and adhere to the principle of least privilege. Securing the underlying data store entities is equally critical because it prevents direct data exposure through accidental misconfiguration. Even if a record type is configured perfectly, if the underlying database permissions are overly permissive, you leave a backdoor that bypasses your application logic. We treat the data store as a foundational layer that must remain shielded, ensuring that only necessary service accounts or specific process execution entities have the required access. When you connect your record to a database table, remember that the Appian infrastructure relies on established service accounts that act as proxies for data interactions. Therefore, checking the Security tab on the data store object itself allows you to audit which developers or system groups have administration privileges, which is a necessary compliance task. By aligning database schemas with Appian-defined security groups, you create a synchronized policy that protects the data fabric as a complete, unified entity. Maintaining these standards requires a recurring audit of your security configurations to ensure they still align with evolving business requirements. As your application grows in complexity, the tendency is to broaden permissions to solve immediate access issues, which is precisely how security vulnerabilities are introduced. Whenever you change a security rule, verify its impact by testing with multiple personas who possess different levels of authority within your system. This strategy of testing ensures that an intended restriction does not inadvertently disrupt core workflows or generate permission errors for end users who require access to function. Remember that while the platform provides powerful tools to manage visibility, the burden of designing a compliant and secure environment rests on your understanding of how these rules interact. Consistent naming conventions and grouped security settings facilitate this, making it easier to identify which objects belong to which security context at a glance. See you in our next session. Welcome back. In this chapter, we will synthesize our data modeling knowledge into performance-first strategies to ensure your applications remain scalable as data volumes grow. When we approach data design in Appian, our goal is to minimize the overhead that the platform incurs when it interacts with your database. One of the most critical aspects of this is understanding the trade-off between flat and nested structures in custom data types, or CDTs. While nesting data might feel natural from an object-oriented programming perspective, Appian's engine often performs more efficiently with flatter structures. Every time you fetch data into the system, the memory consumption is directly tied to the complexity and depth of these structures. By keeping your CDTs flat and normalized, you reduce the serialization cost and allow the engine to process information with significantly less memory pressure. Large, deeply nested objects often lead to bloated memory footprints that can degrade the performance of record lists and complex interfaces. Indexing is another fundamental lever you can pull to ensure your queries execute within sub-second thresholds. It is all too common to see developers build robust interfaces, only to realize that the underlying database queries are performing full table scans because the necessary columns lack appropriate indexes. As your data volume grows, a query that was fast during initial development will inevitably slow down, creating a bottleneck that affects the end-user experience. You should implement indexes on columns frequently used in filtering, sorting, or joining records within your data model. However, remember that indexes are not free. They add overhead during write operations, so you must find the balance. A well-indexed database is the backbone of any performant Appian application, particularly when syncing millions of rows into the data fabric. The introduction of DataSync has changed how we move data into Appian, but it brings the responsibility of optimizing synchronization intervals. We define our sync refresh rates based on the business requirement, but we must be pragmatic about how often we actually pull data from the source. If a specific data entity only changes a few times per day, setting a sync interval of 5 minutes is not just unnecessary. It is a waste of platform resources. Align your sync frequency with the actual volatility of the data to avoid unnecessary stress on your integration layers. Furthermore, avoid the trap of over-syncing large, static lookup tables that could otherwise be handled through cached or less frequent processes. By being intentional with these intervals, you preserve system bandwidth and ensure the data fabric stays lean and responsive. We must also address the common pitfalls related to relationship mapping, which, if mismanaged, can create significant circular dependencies or inefficient query patterns. When you define relationships between record types, ensure that you are selecting only the fields you truly need. and avoiding the mapping of unnecessary metadata. Each relationship contributes to the query complexity, and when these maps become too wide, the platform spends more time calculating joins than returning results. Strive for lean relationships that reflect the specific use cases of your users rather than simply mapping every possible association. Scalability is about foresight, and by constraining the breadth of your data connections early on, you prevent the accumulation of technical debt. An application that remains performant at scale is one that respects the constraints of the underlying hardware and the efficiency of the data retrieval engine. See you in the next lecture. Welcome to the Process Modeling chapter, where we will build the foundation for your automated workflows in Appian. By the end of this section, you will be fully prepared to architect robust processes that drive complex business logic. If you are looking to master the art of business process management, this course is your definitive roadmap to becoming an Appian certified associate developer. You will gain a deep understanding of how to translate real-world requirements into executable process models that are efficient and maintainable. We cover everything from the basic interface navigation to the complexities of activity chaining and process security. By following these lessons, you ensure that your technical skills align perfectly with the rigorous standards required for the ACD 101 exam. The Process Modeler is the central hub where you transform static business requirements into living, automated logic, and its interface is intentionally designed to balance power with accessibility. When you open a model, you are presented with the canvas, which serves as your primary workspace for arranging nodes and connectors, and the palette, which contains the various activity and event nodes you will use. To the right, you find the Properties panel, which dynamically updates based on the object you select to provide control over node logic, assignments, and data flow. You must become comfortable navigating these panels because you will spend significant time toggling between the visual flow and the underlying configuration settings. Efficiency here is not just about speed. It is about maintaining a clean, readable flow that allows other developers to audit your work months down the line. A cluttered or disorganized canvas often indicates a lack of architectural discipline, which can lead to brittle processes that are hard to troubleshoot or scale as business needs evolve. Every process model begins its life cycle the moment a process instance is initiated, moving through a series of nodes until it reaches a terminal event or encounters an error. During execution, the model follows the paths you have defined, processing data and interacting with users or external systems based on the specific logic you have configured. It is important to treat the process display name with care, as this field allows you to use expressions to dynamically name your instances. By embedding identifiers or status information directly into the display name, you drastically improve the monitoring experience for administrators who need to track many running instances at once. You also need to pay close attention to versioning, as every save creates a new version of your model to ensure that you are working on a valid, deployable iteration. Never assume that a process will simply work. You must always verify that your logic maps to a formal process version that is ready for execution within your application environment. Organization is surprisingly important in Appian, and you should consider the folder structure for your models as carefully as you consider your database schema. Placing related process models within clearly defined application folders allows for better security management and makes it significantly easier to package your application for deployment between environments. When you embark on creating your first automated business logic flow, start by mapping out the logical sequence of events, ensuring you have a clear understanding of the start node and the end goal. Use the Properties panel to assign appropriate task owners or to set up data flow, and always perform a validation check before you attempt to test your model. Validating a model identifies missing configurations or disconnected nodes, saving you from the frustration of a process that hangs during execution due to incomplete setup. By maintaining a disciplined approach to these initial configuration steps, you lay the groundwork for reliable software that stands the test of time. I will see you in the next lecture. Welcome back to the section on process modeling, where we will now focus on the fundamental mechanisms of data flow within your workflows. We are going to explore how information moves through your applications, specifically looking at how variables and parameters define the state of a process. In Appian, understanding the distinction between process variables and activity class parameters is essential for building maintainable systems. Process variables act as the global state for a specific process instance, persisting data throughout the entire lifecycle of the workflow from initiation to completion. These variables are scoped to the process model itself and remain accessible to any task or node that belongs to that specific execution path. In contrast, activity class parameters are ephemeral, existing only within the context of a single node or activity. Think of process variables as your long-term storage within the process, while activity class parameters are the local inputs and outputs required for a node to perform its specific unit of work. Managing this distinction correctly prevents memory bloating and ensures that you do not accidentally expose sensitive data across the entire process when it only needs to exist locally. When we discuss the movement of data into and out of nodes, we enter the realm of data mapping. Each activity node in a process model acts as a black box that requires certain information to function, which we provide via the Inputs tab. By mapping a process variable to an activity class parameter, you are essentially creating a bridge that passes the current state of the process into the logic of that specific node. Once the activity completes its execution, we use the Outputs tab to push data back into the process by mapping the results of that activity into our broader process variables. This bidirectional mapping is how we maintain data integrity while ensuring that each step of the business process has exactly what it needs to progress. It behaves much like passing arguments to a function and expecting a return value, except that here, the function is a discrete piece of workflow logic. Concept of scope is perhaps the most significant constraint you will encounter when designing these data flows. If you fail to map data from the output of an activity back into a process variable, that data effectively disappears once the node completes its cycle, rendering it unavailable for downstream tasks. Furthermore, when you are working with user interfaces, you are often interacting with these variables through the SAIL framework. SAIL interfaces have their own local variable scope, which is distinct from the process variable scope, requiring you to map process data into input parameters for your interfaces. When a user interacts with a form, they are modifying the local state of that interface, and you must explicitly define how that state is persisted back to the process engine upon submission. Failing to understand this boundary is a common source of bugs where developers expect data to flow automatically between an interface and a process without a dedicated mapping step. Handling type conversion is another area where precision is required if you want your models to execute without failure. Appian is a strongly typed platform, and attempting to pass a decimal value into a field designed to hold an integer or an array into a single value parameter will lead to execution errors. When mapping between nodes or between an interface and a process, you must ensure that your data structures align perfectly with the definitions of your target variables. If you receive data from an external source or a user, always consider whether you need to perform validation or casting to transform it into the format your business logic expects. By enforcing these constraints at the edges of your process, you minimize the risk of exceptions that interrupt the workflow and require manual intervention from an administrator. Consistent data management is the invisible skeleton that keeps your complex business processes running reliably under load. Talk to you later. Hello, and welcome back. Today, we're going to explore the core components that drive process automation within Appian by examining standard nodes and the critical logic gateways that route your workflow. At the heart of every Appian process model lies a collection of standard nodes that act as the building blocks for your business logic. The start node is your entry point, serving as the trigger that initiates the workflow, while the end node signifies the natural conclusion of the process execution. Between these 2 points, you will frequently rely on the script task node to perform back-end data manipulations, such as updating a record field or calculating a value without human intervention. Conversely, the user task node provides a bridge to the human participants, presenting them with an interface to interact with the process. Configuring these nodes requires a clear understanding of how they consume inputs and produce outputs, as each task must be properly defined to ensure data flows correctly across the process model's lifecycle. You should view these nodes not as isolated silos, but as interconnected steps that maintain the state of your application as it moves from one activity to the next. Once you have your basic nodes in place, the true complexity of your business requirement usually necessitates the use of logic gateways to handle decision-making. The XOR gateway is perhaps the most common, acting as an exclusive choice where the process engine evaluates outgoing paths as a series of Boolean expressions until one evaluates to true. Unlike the XOR gateway, the AND gateway allows for parallel execution, where the token splits to trigger multiple nodes simultaneously, which is ideal for independent tasks that do not rely on each other's output. The OR gateway provides a more inclusive approach, allowing one or more paths to be taken based on the conditions defined on the flow connections. When configuring these gateways, you must ensure that your Boolean logic is robustly written in the expression editor to avoid the common pitfall of having no path evaluate to true, which would cause the process to stall indefinitely. To effectively manage conditional routing, you must master the configuration of outgoing paths, which utilize expressions that return a true or false value. You define these within the flow properties of the gateway, ensuring that the logic accounts for all possible business scenarios, including an else or default path if necessary. For instance, if you're routing an expense approval process, you might use an XOR gateway to send a request to a manager if the total exceeds a certain amount, while automatically completing the task if it falls below that threshold. The expression builder allows you to reference process variables and rule outputs, creating a dynamic environment where the flow of work adapts to the data currently being processed. By meticulously defining these conditional expressions, you ensure that the workflow remains predictable and that each task is routed to the appropriate destination based on the criteria specified by your stakeholders. As you design these flow paths, keep in mind that maintaining readability is just as important as functional correctness, as overly complex decision trees become difficult to troubleshoot later. When multiple gateways are chained together, consider if the logic could be simplified by using a decision object or a standalone expression rule before hitting the gateway. This approach effectively decouples your business requirements from the process structure, keeping your process model clean and easier to maintain. Always test your gateway logic with various datasets during the development phase to verify that unexpected values do not lead to unintended path terminations. By treating your process logic as modular code, you build a sustainable foundation for your application that can handle the nuance of real-world business requirements with ease and consistency. I will see you in the next lecture. Welcome to the chapter on implementing user tasks and routing, where we will translate business requirements into actionable work for end users within Appian. In the Appian process ecosystem, a user input task is the fundamental bridge between an automated workflow and human decision-making. When you place a user input task node on your process modeler canvas, you are telling the system to pause execution and surface an interface to a specific actor. Before a user can interact with this task, you must define the assignment configuration, which is arguably the most critical step in ensuring the process flows to the right person. You can assign tasks to individual users by their username or to groups through group constants, which is the preferred best practice for scalability. Assigning to a group allows you to maintain organizational roles dynamically without changing the process model every time personnel changes occur within your business department. Once assigned, these tasks appear directly in the user's tempo task list or the task portal, ready for action. The Assignment tab within the User Input Task Properties is where you control precisely who sees the task and how they interact with its lifecycle. You might decide to assign the task to a specific user using a process variable, or perhaps you want to utilize the concept of swim lanes if your process diagram benefits from that visual organization. Beyond simple assignment, you must consider the task's priority and deadline attributes to ensure that critical work items receive appropriate visibility. Higher priority tasks bubble up naturally in a user's task list, while the deadline field allows you to schedule automated escalation actions. Escalation is a powerful feature that allows you to trigger a secondary path or notification if a user fails to act upon a task within a specified timeframe. This ensures that your business processes do not stall due to human latency, keeping the overall system throughput predictable and efficient. Notifications play a supportive but essential role in bridging the gap between passive waiting and active engagement. Within the node configuration, you can enable task notifications that automatically email the assignee, alerting them that an action is required within the system. While these emails act as a reminder, they should be used judiciously to avoid notification fatigue among your user base, as frequent, unnecessary pings often lead to ignored requests. Furthermore, Assigning tasks to groups introduces the concept of task claiming, where any member of the group can take ownership of the item to start the work. Once a task is claimed, it is removed from the general pool of the group, preventing multiple users from performing redundant work on the same record. The combination of clear assignment, strict deadlines, and targeted notifications creates a robust framework for managing human-centric activities within your automated workflows. I will see you in the next lesson where we continue our exploration of process modeling. Welcome back to our discussion on architecting robust workflows through modularity. In this session, we will examine how subprocesses allow us to decompose monolithic logic into maintainable, discrete units. When we approach process design, it is tempting to build a single, sprawling process model that handles every possible transition and logical branch. However, such designs quickly become unmanageable as stakeholders request changes or as technical requirements evolve. By utilizing the subprocess node, we shift toward a modular architecture where specific business functions are encapsulated within their own distinct life cycles. This practice mirrors the principle of separation of concerns in traditional software development, where we strive to keep components small, cohesive, and focused on a single responsibility. Not only does this approach significantly improve the readability of your diagrams for other developers, but it also aids in troubleshooting when a specific segment of the workflow fails. Instead of navigating a massive, tangled web of nodes and gateways, you can isolate issues to a specific subprocess. Furthermore, modular design allows you to reuse these process logic segments across multiple parts of an application, or even across different applications entirely. This reduces the duplication of effort, ensuring that if a business rule changes, you update it in one central location, rather than hunting through dozens of processes to apply the same hotfix. The choice between synchronous and asynchronous execution is fundamental to how your processes behave under load and how they respond to exceptions. When we configure a subprocess to run synchronously, the parent process effectively pauses and waits for the child process to complete its lifecycle before proceeding to the next node. This is essential when the parent process requires output data from the subprocess to continue its own execution flow correctly. Conversely, asynchronous execution allows the parent process to trigger the subprocess and immediately move forward without waiting for a completion signal. This approach is highly performant in scenarios where the child process performs background tasks like sending notifications, logging audit data, or updating non-critical records. You must be careful choosing between these, as synchronous overhead can impact the perceived performance of a user-initiated process if the subprocess takes a long time to finish. Always evaluate whether the parent actually needs the subprocess results immediately, or if the subprocess merely needs to happen eventually as part of the overall application state. Beyond timing, we must consider how to dynamically trigger these processes using either the by-process model or the by-expression configuration. Selecting a process model directly is the most straightforward method, ideal for static workflows where the process to be invoked is known at design time. However, using a process model expression provides a layer of indirection that can be incredibly powerful in complex enterprise systems. When utilizing an expression, you can write conditional logic that determines, at runtime, which process model should be executed based on variables or user input. This level of flexibility allows for highly adaptive workflows that react to input in real time, effectively allowing developers to create factory-like patterns in their automation logic. While the flexibility is high, it also introduces complexity in terms of configuration and debugging, so it should be reserved for scenarios where standard static links are insufficient. Keeping your logic as simple as possible is always the goal, but understanding these dynamic options is necessary to pass the exam and build truly enterprise-ready software. Focusing on memory management is another critical aspect of breaking down large processes into smaller components. Every process instance consumes engine memory and storage, and when you maintain a massive monolithic process, it holds on to references and variables for as long as that instance is active. By delegating tasks to sub-processes, you allow the engine to clean up completed segments more efficiently, potentially reducing the footprint of any single instance. This is particularly important when dealing with high-volume processes that could otherwise lead to system performance degradation or timeout issues. When you design with modularity in mind, you implicitly manage the lifecycle of your variables, ensuring that data is passed into the subprocess context only when needed and cleared shortly thereafter. Think of this as garbage collection for your process orchestration, where keeping your variable scope tightly prevents the environment from bloating unnecessarily over time. See you in the next lecture. Welcome back. In this session, we will examine the critical balance between process model security and the architectural performance constraints required for enterprise-grade applications. When we talk about process security, we are primarily dealing with the access control list defined on the process model object itself. Appian categorizes permissions into distinct roles, such as administrator, editor, viewer, and importantly, the initiator versus the standard user. An initiator is the user who triggers the process instance, and their rights are often elevated within the context of that specific process execution. In contrast, the process designer role implies authoring capabilities, allowing users to modify the model structure and logic. Managing these roles correctly is vital, as overly permissive settings can expose business logic or sensitive data to unauthorized internal actors. You must always adhere to the principle of least privilege, granting only the granular permissions necessary for a user to perform their specific operational tasks. Process visibility determines who can monitor instances once they are in flight, which is an often overlooked aspect of security. Within the Security tab of a process model, you define who has the rights to view, cancel, or pause instances of that model. If you allow too many users to view process history, you inadvertently increase the cognitive load on the monitoring interface and potentially expose PII if the process variables are not properly masked. Monitoring permissions should be restricted to process owners or system administrators who actually need to troubleshoot or audit execution paths. This isolation prevents accidental interference with running processes and maintains a clean separation between those who consume the service and those who maintain its integrity. System health is inherently tied to how we handle the life cycle of a process instance after it has completed its execution. Appian provides two primary mechanisms for cleanup: archiving and deleting, each serving a different purpose in your maintenance strategy. Archiving preserves the process data in a compressed format that is no longer active in the engine's primary memory, thus reducing the footprint on the server. Deleting, conversely, removes the instance entirely, which is appropriate for data that has reached the end of its legal or business retention cycle. Failing to configure these policies properly will lead to memory bloat, where the execution engine struggles to manage thousands of active or dormant instances, ultimately slowing down the entire environment. Performance in high concurrency environments requires a disciplined approach to process design, specifically regarding the variables we instantiate. Every active variable, especially large objects like CDTs or collections and process variables, consumes memory in the execution engine. Developers often fall into the trap of over-relying on process variables when local variables in an interface or a compact expression calculation would suffice. To avoid memory leaks and degraded performance, you should keep process variables lean and scoped to their actual requirements. When a process runs, the system keeps the state of these variables in memory, so unnecessary data bloat directly translates to longer wait times and potential system instability during periods of peak load. Retention policies must always be aligned with both the business requirements and the technical performance constraints of your specific Appian instance. Business analysts might request that every historical process instance be kept indefinitely for audit purposes, but this strategy ignores the physical reality of disk space and index performance. You need to mediate these expectations by implementing periodic archiving jobs that move older data to a secondary storage location or a separate reporting data store. By separating the historical audit trail from the active process engine, you ensure that the high concurrency performance remains predictable. A well-tuned system is one where the engine is only concerned with active, relevant work, rather than wading through petabytes of legacy process metadata. The intersection of security and performance is not just about permissions and memory. It is about the entire lifecycle management of your business processes. By carefully defining who can initiate, view, and modify process models, you create a robust security perimeter that limits the surface area for errors or misuse. By implementing thoughtful archiving and deletion strategies, You ensure that the server remains performant and responsive regardless of how many thousands of processes pass through the system each day. These considerations are fundamental to building scalable solutions that respect both the constraints of the platform and the needs of the business users. Always evaluate your design choices through the dual lenses of access restriction and resource efficiency to build truly production-ready applications. I will see you in the next lecture. Hello, and welcome back to our deep dive into the technical intricacies of Appian development. Today, we are turning our attention to one of the most critical aspects of process design, activity chaining. When we model business processes in Appian, we often require a sequence of tasks to happen as a unified, fluid motion for the end user. Activity chaining is the mechanism that allows us to connect a series of nodes within a process model so that the system treats them as a single interactive session. Without chaining, the process engine pauses at every user input task, pushing the user back to their task list or the interface dashboard before they can proceed to the next step. By enabling chaining, we effectively extend the user session across multiple nodes, ensuring that once they submit a form, they are immediately presented with the next form in the workflow. This is essential for creating professional applications where the administrative overhead of navigating between menus is removed from the user experience. You should view chaining as a bridge that maintains the state of the process for the user while they move through a logical sequence of actions. To implement activity chaining, you manually configure the properties of the connection lines between nodes in your process model, or you select the chaining option directly on the user input task itself. Once enabled, the process engine monitors these chained nodes, essentially keeping an open thread that reserves the process context for that specific user. However, this convenience comes with strict technical constraints that you must respect to ensure the stability of the platform. There is a hard limit of 50 nodes in an activity chain, which is a built-in safety mechanism designed to prevent memory leaks and infinite loops. If you attempt to chain more than 50 nodes, the process will fail to trigger the subsequent tasks in the chain, leading to a broken user experience. Furthermore, each chain node consumes resources differently than an asynchronous node, as the system must maintain the session state in active memory until the chain concludes or hits an unchained node. Developing a robust application requires you to use chaining judiciously rather than reflexively for every transition in a model. While it makes the flow more intuitive for the user, excessive or unnecessary chaining can lead to performance degradation if your process models are overly complex. Always consider whether a user actually needs to complete 3 concurrent forms in one sitting, or if it is functionally acceptable to allow them to revisit their task list. Think of chaining as a specialized tool for tight, high-touch workflows where context switching would be disruptive rather than helpful. When you decide to chain, ensure that every node in that sequence is optimized for speed, as the user is effectively waiting for the server to process the transition before the next interface renders. If one node in the chain is slow, the entire flow feels sluggish to the user, highlighting the importance of efficient expression logic and clean data handling within those specific nodes. Remember that the process engine will automatically break an activity chain if it encounters a node that is not configured to accept the chain, or if the chain length exceeds the prescribed limit. You must also be mindful of security and node-level configurations, as a chained flow will maintain the identity and scope of the individual who initiated the sequence. If you have complex logic or secondary processes that do not require user interaction, it is usually better to handle those asynchronously outside the chain sequence. This allows the system to balance the load more effectively and ensures that the user-facing part of your application remains responsive and light. By separating user-critical steps from back-end automation, you maintain a cleaner architecture while still providing that seamless, integrated experience that Appian is designed to support. See you in the next lesson. Welcome back. In this lesson, we will focus on the practical application of monitoring and debugging running process instances within the Appian environment. When a process model moves from the design phase to the production environment, the ability to observe its behavior becomes critical for maintaining system reliability. The primary tool at your disposal is the process monitoring view, which serves as a window into the live state of your automated workflows. By navigating to this interface, you can isolate specific instances, even those that have entered an error state, or are performing unexpectedly. This view provides a high-level overview of active, completed, and paused processes, allowing you to filter by status or date range to narrow your search. Once you select a specific instance, you can enter Monitor mode, which transforms the canvas into a diagnostic workspace. This mode reveals exactly which nodes have executed, which paths were taken through XOR or OR gateways, and where the process currently resides. Inside Monitor mode, the most powerful feature is the ability to inspect the real-time values of process variables. Frequently, logical errors arise not from the workflow design itself, but from the data being passed between nodes or the output of complex expressions. By selecting an individual node, you can view its instance properties, including the specific input and output values at the moment of execution. This is where you will identify common pitfalls, such as type mismatches, where a text input is unexpectedly passed to a numeric process variable, or null values causing expression failures. If you find that a node has failed due to a transient issue, or if you simply need to correct a variable value after fixing a logic error, you can modify the variable directly if the process is paused. Being able to inspect these values saves significant time compared to recreating the entire process flow within the modeler, as it gives you the exact snapshot of data that led to the fault. Beyond simple variable inspection, the process history log is an invaluable resource for understanding the chronological sequence of events. The logs capture every state change, user interaction, and system-level execution, providing a trail that is essential for auditing business outcomes. If a process stalls, you can check the node logs to see if a particular service task returned an error code or timed out while waiting for a response from an external system. For nodes that have failed, the platform often allows you to restart the specific node once the underlying issue has been resolved, such as fixing a broken connection or updating a data store entity. This capability prevents the need to cancel an entire process instance and start over, which is particularly beneficial for long-running workflows that might involve multiple human participants. By carefully interpreting these logs, you ensure that your business logic is not only running but also interacting with the broader system architecture as intended. Effectively managing these tools requires a methodical approach to software maintenance, where you view the monitoring console as an extension of your development environment. Instead of reacting to production issues as emergencies, you should treat the process history as documentation of how your code behaves under real-world conditions. When you encounter an expression failure, resist the urge to simply restart the node without investigation, as this will likely result in the same error recurring. Instead, always evaluate the inputs using the same expression logic you defined in the modeler to confirm where the data integrity breaks down. As you gain proficiency in reading these dashboards, you will find that the feedback loop between spotting an issue and deploying a resolution becomes significantly tighter. Consistent use of these diagnostic patterns is what separates a novice developer from one who can confidently support complex, enterprise-grade orchestrations. See you in the next lecture. Welcome to this chapter on the SAIL framework, where we will demystify the core of Appian user interface development. We are going to explore how SAIL enables you to build powerful, responsive interfaces that work seamlessly across any device. SAIL, which stands for Self-Assembling Interface Layer, is the fundamental engine that powers every user interaction in an Appian application. It is inherently declarative, meaning that instead of writing imperative code to manipulate DOM elements or handle low-level event listeners, you describe the desired state of your interface through configuration. When you define an interface in Appian, you are providing a set of instructions that the platform translates into a functional user experience. Because the platform understands the structure and the intent of your components, it takes on the heavy lifting of rendering those components into HTML or native mobile elements based on the client device. This abstraction is exactly what allows us to adhere to the principle of build once and deploy anywhere, saving us from writing specialized code for different target platforms or screen orientations. When you open the Interface Designer, you are presented with a primary workspace that offers two distinct modes for development, known as Design and Expression. The Design mode provides a visual, drag-and-drop environment that is excellent for prototyping or structuring complex layouts without needing to memorize the specific syntax of every component. As you drag components into the canvas, the underlying SAIL code is automatically generated for you, reflecting your visual changes in real time. On the other hand, the expression mode allows you to work directly with the underlying expression language, which is where you will spend most of your time as a professional developer. This mode provides granular control over object properties, conditional logic, and the wiring of data between your inputs and the rest of your application. Mastering the transition between these two modes significantly increases your productivity, as you can leverage the speed of visual layout while retaining the precision of manual expression writing. The declarative nature of this architecture ensures that your application remains maintainable and robust as your business requirements evolve. By avoiding the manual manipulation of UI state, you reduce the surface area for common bugs that typically arise when components get out of sync with their underlying data. The Sail engine acts as a mediator, constantly monitoring the state of your application and reevaluating the interface expressions to ensure that the visual representation accurately matches the current record values or process variables. This lifecycle management is managed entirely by the server, which serves only the necessary UI updates to the client. Consequently, you are spared from the complexities of managing network requests, state serialization, or browser-specific rendering quirks that often plague traditional web development. I look forward to discussing how we can leverage these layouts in the next video. Welcome back. In this chapter, we explore how to construct professional and responsive user interfaces using the Sail framework's layout and navigation components. Building a functional interface in Appian is much like constructing a sentence. If you neglect the structure and the flow, the meaning becomes obscured. When we talk about layouts, we are primarily concerned with how components occupy space and how they communicate spatial hierarchy to the end user. The form layout functions as the primary container for data entry, establishing the boundaries of our workspace and providing a consistent experience as users interact with our systems. By nesting components within a form layout, we ensure that elements remain anchored, which is critical when developing complex forms that require field grouping. A common mistake is to ignore the nesting hierarchy, which leads to disjointed interfaces that feel fragile rather than engineered. As you develop these forms, remember that their primary goal is to guide the user towards a successful completion of their task while minimizing cognitive load. Dashboard layouts serve a different purpose, typically focusing on information consumption rather than data input. While a form layout dictates rigid input expectations, a dashboard layout offers the flexibility needed for high-level data visualization and status monitoring. To organize content effectively within these dashboards, we utilize section layouts, which act as conceptual buckets that group related information into discrete, digestible areas. By applying distinct headers and background colors to these sections, we can visually segment complex reports into manageable parts. Furthermore, card layouts provide an excellent mechanism for styling containers, allowing us to elevate specific content blocks to draw the user's attention. Think of these tools as the scaffolding of your application, where each piece serves a specific communicative function. Responsive design is no longer an optional feature. It is an inherent property of the Sail framework that we must design for proactively. When we arrange components in a column layout, Appian calculates the horizontal space available and attempts to maintain that side-by-side arrangement as long as the viewport remains wide enough. However, once the available screen width drops below a specific threshold, such as when a user accesses your application on a mobile device, stacked behavior automatically takes over. If you design with the assumption that fixed widths will always hold, you will inevitably encounter broken or illegible interfaces when viewed on smaller devices. We use column weights to define relative proportions, ensuring that content expands and contracts gracefully without losing its intended relationship to other elements on the screen. Sidebars are often misunderstood, frequently being treated as an aesthetic choice rather than a functional navigation tool. When implemented correctly, a sidebar provides persistent context for the user, ensuring that primary navigation or secondary information remains accessible regardless of how far down a page the user is scrolled. However, because sidebars consume horizontal real estate, they should only be used when they add significant value to the user's workflow. If adding a sidebar crowds your main content area to the point where data becomes unreadable, it is a sign that your layout strategy needs to be recalibrated. Proper navigation design requires a balance between accessibility and content density, always prioritizing the clarity of the task at hand over the convenience of a persistent menu. Consistency is the hallmark of a professional interface, and this is achieved through the disciplined use of layout patterns across your entire application suite. Rather than reinventing the visual structure on every single interface, aim to create a predictable sequence of content blocks that users can learn to navigate intuitively. Use sections to establish a visual rhythm, and utilize cards to demarcate boundaries for information that might otherwise blend into the background. As you gain more experience, you will find that the most effective interfaces are often the ones where the layout disappears entirely, allowing the user to focus exclusively on the record data or the process task they are performing. Always test your layouts by resizing your own browser window during the development phase to anticipate how the stacking behavior will impact the user experience. I will see you in the next lecture. Welcome back to our exploration of the SAIL framework, where we turn static layouts into functional, interactive experiences. In this session, we will focus on capturing user input and ensuring that the data flows reliably into your business processes. Building effective user interfaces starts with selecting the right input component for the data you intend to collect. Appian provides a rich palette of widgets such as text fields for free-form input, drop-down lists for selecting from a predefined set, date pickers for calendar-based entries, and radio buttons for mutually exclusive choices. Each of these components acts as a bridge between the front-end user experience and your underlying data structure. To make them functional, we must bind them to rule inputs or local variables, which act as the storage containers for the user's intent. When a user interacts with a field, the value is captured, and the bound variable updates in real time, allowing for a reactive interface that responds immediately to user actions. It is a fundamental design principle that the component's value parameter must point directly to the data structure that the downstream process expects to receive. Once we have established the connection between the UI and our data, our next responsibility is to ensure the integrity of that data through validation. Simply collecting input is rarely sufficient. We must enforce business rules to prevent invalid or incomplete information from reaching the database. The most straightforward approach is using the required property on components, which provides an immediate visual cue that a field cannot be left blank. However, real-world scenarios often require more nuanced logic than a simple check for emptiness. By using the validations parameter, we can define custom expressions that evaluate the state of an input against specific constraints. For instance, you might want to ensure a price is positive, a date is not in the past, or a text string meets a specific pattern. Because SAIL is inherently reactive, these validation expressions are re-evaluated whenever the input changes, providing the user with immediate, context-sensitive feedback. Designing for data entry also requires a thoughtful approach to user experience and technical efficiency. Sanitizing input is often handled by the framework itself, but the logic you construct in your validation expressions serves as your primary defense against bad data quality. It is a best practice to keep validation logic concise and readable, perhaps by placing complex rules into separate expression rules rather than embedding them directly within the interface component. This makes your UI code cleaner and allows for easier unit testing of the business logic independent of the visual layout. Remember that a validation message should be clear, instructive, and helpful, guiding the user towards a correct entry, rather than simply flagging an error. When the user eventually submits the form, you can be confident that the data has been cleansed and validated against your defined constraints, ensuring smooth processing in the backend. See you in the next lecture. Welcome back, everyone. Today, we are stepping into the core of dynamic SAIL interfaces by examining how local variables and reactive components allow us to shape user experiences in real time. When we build professional interfaces in Appian, we rarely deal with static forms that never change. Instead, we need a mechanism to maintain state within the interface itself, distinct from the global process or data variables. This is the primary role of the local variables function. Think of this function as the scoped container for all your transient data. It allows you to declare variables that exist only for the life cycle of that specific interface interaction. If you assign a value to a local variable, that value is maintained during the user's session, allowing for instantaneous UI updates. By isolating state, we keep our components clean and maintainable, preventing the leaking of data into scopes where it does not belong. This approach is essential for building responsive applications that feel snappy and intuitive to the end user. The true power of local variables emerges when we pair them with automated refresh behaviors. Through the refresh variable configuration, you gain granular control over when a variable recalculates its value. We can define refresh criteria based on changes to other variables or even set periodic intervals for background updates. For instance, if you are calculating a total based on a user-selected number of items, the refresh always parameter ensures that every time the input changes, your variable reevaluates. This reactivity is what eliminates the need for full-page reloads, providing a seamless experience similar to modern web frameworks. When configured correctly, these variables act as a reactive data backbone, ensuring that the UI always displays the most accurate state without requiring unnecessary round trips to the server. Beyond data calculation, we must address the user experience through the lens of conditional visibility. The show. When parameter is the standard way to toggle the visibility of any component based on the evaluation of an expression. By referencing a local variable, perhaps one that tracks a Boolean flag or a selected drop-down value, you can show or hide entire sections of a form dynamically. If a user selects a specific option from a checkbox, you might reveal a set of secondary text fields that were previously hidden. This keeps the interface clean by only presenting relevant information, reducing cognitive load on the user. Because this is handled client-side, the transition is smooth and immediate, reinforcing the perception of a well-architected, highly responsive application. Refining these interfaces requires a disciplined approach to managing the variables themselves. You want to avoid over-declaring variables that do not serve an immediate purpose, as this can lead to unnecessary complexity. Instead, focus on defining variables that support specific UI state requirements, such as filtering results or formatting input for a user. By nesting your logic within the parameters of your components, you can leverage the local scope to pass updated values down the tree of components effortlessly. Keep in mind that every time a variable refreshes, the components referencing it will reevaluate, so efficiency in your expressions is still a technical necessity. Balancing reactivity with performance is the mark of a skilled developer, and it begins with understanding these fundamental scoping rules. See you in the next lecture. Welcome back to our discussion on crafting effective user interfaces within the Appian Sail framework. Today, we focus specifically on mastering the implementation of grids to display and interact with tabular data. In Appian, the primary component for displaying tabular data is the A grid field. While the platform has evolved to prioritize record-backed grids, understanding the underlying grid component remains essential for anyone tasked with building custom user interfaces. At its core, a grid is a container that maps a data source to a set of columns, which you define using the aGridColumn function. You must be precise with your column definitions, as they act as the interface between your raw data source and the human who needs to read it. Each column requires a header label and an expression that extracts the relevant field from your data provider. If you are binding to a record type, the grid is significantly more performant because it leverages the underlying data sync architecture. You should always aim to use the record-backed configuration whenever possible to ensure that sorting, filtering, and pagination are handled efficiently by the platform engine rather than through expensive client-side calculations. Handling large datasets effectively is a hallmark of a proficient Appian developer. When you display hundreds or thousands of rows, you cannot simply dump the entire result set into the user's browser, as this will lead to catastrophic performance degradation. Instead, you must configure the paging info parameter within the grid configuration to fetch only a subset of data at a time. The paging mechanism, defined by paging info, instructs the system to request only the rows needed for the current view, such as the first 20 or 50 records. This is vital for maintaining a responsive user interface that does not lock up when a user navigates between pages. You should also consider the user's need to sort or filter this data. By enabling grid-level sorting, you allow the engine to perform these operations at the database or sync layer level, which is substantially faster than sorting within the interface component itself. Row selection is another powerful feature that transforms a static display into an interactive tool. When configured with a selection value and a selection save into parameter, the grid provides a way for users to pick specific records for further action, such as bulk editing or deleting. From a technical perspective, the grid stores the identifiers of the selected rows in a local variable, which your other components can then reference to drive further logic. You must carefully manage this selection state, ensuring that the selected items are properly cleared if the user navigates away or performs a secondary search. If you are building an editable grid, you enter a different paradigm where you must manage individual row state changes via local variables or a process-backed approach. Because editable grids require more complex validation logic to ensure data integrity, I strongly recommend keeping the logic for updating those fields as clean and modular as possible by leveraging separate expression rules for your validation logic. Optimizing interface performance is not just about keeping the display snappy, but also about being respectful of the network and server resources. Every column you add to a grid increases the payload size and the complexity of the rendering engine. If a column's expression involves complicated logic or multiple cross-references, you will notice a latency spike as the grid initializes. To mitigate this, pre-calculate as much data as possible before it reaches the interface. For example, if you need to concatenate a user's first and last name, perform this transformation in your query or your expression rule rather than inside the grid column definition itself. By keeping the interface layer as thin as possible, you ensure that the load times remain consistent regardless of the underlying data volume. You are essentially building a window into the data rather than attempting to house the entire warehouse directly inside the user's view. See you in the next lecture. Hello. Today we are exploring the visual side of the SAIL framework by focusing on charting and data visualization techniques. This chapter is designed to transition you from building static data entry forms to crafting dynamic, insightful dashboards that serve executive needs. In this chapter, we will master the art of transforming raw record data into intuitive visual representations using bar, pie, line, and KPI components. You will learn how to leverage Appian's native charting library to build interfaces that not only display numbers, but also tell a cohesive story about business operations. We will look at the mechanics of aggregating data efficiently, ensuring that your dashboard remains performant even when dealing with large record sets. By the end of this journey, you will possess the expertise to translate complex business requirements into professional, high-impact user interfaces. If you want to elevate your status from a functional developer to a valued partner in the business decision-making process, this focused deep dive is exactly what you need. When we approach data visualization in Appian, the first step is always understanding the nature of the data you intend to project. A chart is only as effective as the underlying query, so we must rely heavily on the query record or aggregation functions to shape our data before it reaches the UI component. When you utilize the bar chart component, for example, your objective is typically to compare discrete categories, such as the total volume of support tickets grouped by priority level over a specific quarter. You should always ensure that your grouping dimensions are clear and that your aggregation functions, such as sum or average, are applied to fields that provide genuine utility to the user. It is tempting to crowd a dashboard with multiple charts, but design discipline dictates that you should prioritize clarity by ensuring your labels and legends are concise and descriptive enough for a layperson to interpret at a glance. Interactivity is what differentiates a standard graphical report from a functional Appian dashboard. By configuring drill-down capabilities, you allow end users to move from a high-level summary directly into the granular record details that explain the underlying trend. You achieve this by mapping links to specific chart segments, which can open related records in new views or trigger specific process actions. For instance, if an executive notices an unusual spike in a line chart representing departmental spending, a well-placed link should allow them to navigate immediately to the expense items causing that anomaly. This creates a closed loop where the user is never left with a question that they cannot immediately investigate, turning a static image into a functional tool. Always remember that the goal is to reduce the cognitive load on the user. Therefore, keeping your drill-down paths logical and predictable is a fundamental aspect of professional interface design. Choosing the correct visualization type is a foundational skill that avoids misleading your audience. A pie chart is excellent for showing proportions of a whole, but it becomes virtually unreadable if you have more than 5 or 6 data categories in your dataset. In such scenarios, a horizontal bar chart is often a much more readable alternative because it provides a consistent visual baseline for comparison and gives you more room for explicit axis labels. KPI components, on the other hand, are best utilized for highlighting a single, critically important metric that requires immediate attention from the user, like current monthly revenue or open critical vulnerability counts. You should use color palettes consistently across your entire application to denote statuses, keeping in mind that certain colors like red, yellow, and green carry strong cultural connotations of urgency or safety. By maintaining this consistent design language, you reduce the learning curve for business users who may switch between different dashboards frequently throughout their workday. Finally, we must consider the technical constraints of data aggregation when building these interfaces. Sale interfaces are evaluated on the server, and performing overly complex manipulations inside the interface definition itself can lead to latency and poor user experience. You should aim to use record type level aggregations or expression rules to pre-process data into the desired format before passing it to the charting functions. This separation of concerns ensures that the interface remains focused on layout and presentation rather than heavy data processing. If you find your charts loading slowly, review the efficiency of your source query and ensure you are not fetching more data than is required for the initial view. By keeping your data fetching logic lean and offloading the heavy lifting to the back end, your dashboards will remain responsive and professional for even the most demanding users. I will see you in the next lecture. Welcome back. Let's discuss optimizing sale interfaces to ensure your applications remain responsive and user-friendly. In this module, we will explore the critical strategies needed to maintain high performance in your Appian interfaces. Building high-performance interfaces in Appian requires a disciplined approach to how you handle data retrieval and expression evaluation within your sale code. Every piece of logic you write executes either synchronously or asynchronously, affecting the perceived latency of the user interface. When we talk about performance, we are primarily concerned with reducing the round-trip time between the Appian server and the end user's browser. You must prioritize minimizing the number of intense computations or data queries that occur during the initial render phase of a screen. If an interface feels sluggish, the first place to look is the sheer volume of data being processed before a component is even rendered. By carefully managing your local variables and avoiding redundant expressions, you can create a streamlined experience that feels instantaneous to the user. The Interface Designer provides a Performance tab, which is your most valuable tool for diagnosing bottlenecks. When you open this tab, you see a breakdown of execution times for every rule and data query contained within that interface. It is important to look for high-duration values, as these indicate expressions that are straining the system. If you see a particular rule taking up a significant portion of the total execution time, that is a clear signal to refactor your logic. You should also pay attention to the number of calls being made to external data sources. Each query adds an overhead, and chaining too many calls creates a cumulative delay that impacts overall UI responsiveness. Using the Performance tab allows you to move away from guesswork and focus your optimization efforts where they have the most tangible impact. One of the most effective strategies for performance involves understanding variable scope and refreshing patterns. While legacy code often relied on local variables declared within refresh blocks, modern Sail allows for more efficient state management. Every time a dependent variable changes, the entire interface logic reevaluates, which can quickly lead to what we call heavy expressions. To combat this, you should aim to minimize the complexity of your calculations by breaking large, monolithic expressions into smaller, reusable rules. Avoid putting high-latency queries directly inside a loop or a functional component that triggers multiple times during a refresh cycle. By caching data where appropriate and only pulling what is strictly necessary for the current view, you significantly reduce the load on both the client and the backend. Strategic use of expressions also matters when it comes to nested logic and data manipulation. Whenever you find yourself writing deeply nested loops or recursively querying data grids, you are likely creating a performance bottleneck. Instead of recalculating values on the fly every time an input field changes, try to perform your data transformation once at the process level or within the data source itself. Appian's record types are designed to handle data relationships efficiently, so leveraging those instead of manual query functions usually yields better performance. Remember that every expression must be parsed and executed by the engine. So, cleaner, flatter code is almost always faster. Focus on modularity and efficiency, and your interfaces will remain stable even as your application complexity grows. See you in the next lecture. Welcome back. In this lecture, we look at the mechanics of modular UI design in Appian by focusing on reusable interface components. Achieving consistency across a large application requires moving away from monolithic interface files toward a more compositional approach. When you build a complex system, you often find yourself recreating the same visual elements, such as standardized headers, footers, or custom picker components, on multiple forms. By extracting these elements into individual interface objects, you adhere to the DRY principle, which stands for don't repeat yourself. This practice is not merely about writing less code. It is fundamentally about centralizing your maintenance surface. If your business requirements change, you only need to update the logic or styling in one interface definition to propagate those changes everywhere that component is utilized. This significantly reduces the probability of introducing inconsistencies or bugs when scaling your application across different business units. To turn an interface into a reusable component, you must define the contract through which it interacts with its parent. In Appian, this is accomplished primarily through rule inputs. When you define a rule input in a child interface, you are effectively declaring the data dependencies that the interface requires to render correctly. Think of these rule inputs as the parameters of a function in a programming language. You define the type, such as a text, number, or a custom data type, and you could even set them as arrays if the component needs to handle multiple entries. When referencing this child interface from a parent form using a load or with variable scope, you map local variables or specific data fields directly to these rule inputs. This mechanism ensures that the child component remains decoupled from the specific context of the parent, making it highly portable and robust. Consider a scenario where you have a custom address selection component that performs complex validation and lookup. Instead of embedding the layout and the query entity logic directly into every page that requires an address, you build a single interface dedicated to this functionality. You pass the relevant address object as a rule input, and the component manages its own internal state and display logic. If the downstream address API changes, or if you decide to add a new lookup field for postal codes, you perform this change in one centralized location. This composition allows for cleaner parent interfaces that are easier for other developers to read and understand. By organizing your interface library into logical folders, you also improve discoverability for your team, turning UI development into a methodical assembly process rather than repetitive manual scripting. Maintaining a library of standard components also allows for strict enforcement of corporate-style guidelines without requiring every developer to memorize every design token. When you encapsulate a button group or a header within a reusable component, you bake the necessary margins, padding, and color schemes into the definition itself. Even if the underlying Appian sale functions update or evolve, your components remain anchored to the design specifications you settled on initially. This abstraction layer acts as a buffer between the raw UI logic and the final form render, which is essential for managing the long-term technical debt of an enterprise application. As you progress through your development lifecycle, you will see that this investment in modularity pays off almost immediately, in the form of accelerated development velocity and a much more polished end-user experience across the entire system. I will see you in our next session. Welcome to this chapter regarding the foundations of the Appian expression language. In this section, we will establish the fundamental syntax and structures required to build robust logic across your applications. In this chapter, we will master the Appian expression language, which is the programmatic heart of the platform. We will explore everything from basic syntax and data types to calling functions and utilizing domain prefixes like rule and fn. Mastering these fundamentals is the single most effective way to elevate your development practice and pass the ACD 101 exam with confidence. By the end of this journey, you will possess the clarity and technical precision needed to write maintainable code that powers sophisticated business solutions. If you have spent time in other programming environments, Appian's expression language will feel familiar yet specialized. At its core, the expression language works through function calls, which are structured as a function name followed by arguments encased in parentheses. You might recognize this as essentially a Lisp-derived syntax, where composition and evaluation of data are paramount. We represent data using standard types such as strings, which are wrapped in double quotes, integers, decimals, and booleans. Booleans in Appian are represented as constant values, specifically true or false, and they serve as the backbone for all conditional logic you will write. When you are editing these expressions, the interface provides a powerful autocomplete service that helps you discover available functions and variables without constantly switching context. It is a tool that rewards the developer who understands the underlying data structures being passed between these functions. The most critical aspect of writing expressions involves understanding domains, specifically the distinction between the FN and rule prefixes. The FN domain encompasses the vast library of standard functions provided by the platform, such as mathematical operations, date manipulations, or list processing. When you type FN, the expression editor immediately suggests these built-in helpers, allowing you to manipulate strings or aggregate data arrays effectively. Conversely, the rule domain refers to custom expression rules you have authored yourself, which encapsulate reusable logic for your specific business case. By prefixing these custom rules, you ensure the platform can distinguish between standard system logic and the bespoke logic your team has built to handle domain-specific requirements. Keeping this distinction clear leads to better code discoverability and helps prevent collision between native functions and custom developments. Effective development in Appian requires a disciplined approach to how you structure your logic blocks. Instead of writing monolithic lines of code, you should aim to make your expressions readable by leveraging the editor's formatting features. Think of an expression as a chain of transformations where the input is transformed through several functions before reaching the desired output. Since Appian expressions are strictly evaluated, the order of operations matters significantly, just like in any functional programming language you might have used before. When you work with lists, you will often use functions that iterate over those lists, which requires a deep understanding of how variables are scoped within these operations. The more you rely on the built-in documentation provided directly within the expression editor, the less time you will spend navigating away from your work to look up function signatures. Consider how you handle null values, which is a common source of runtime errors in complex applications. In this ecosystem, a null value is not just an empty string or a zero, but an absence of data that can propagate through your functions if not handled explicitly. You should frequently employ functions like isNull or the property function to safely navigate through data structures, especially when dealing with query results or complex nested objects. Treating data with this level of caution is the hallmark of a senior developer who understands that robust applications are built on defensive coding practices. By checking for the presence of data before attempting manipulation, you drastically reduce the surface area for bugs to emerge in your process models and user interfaces. This habit of defensive coding will serve you well, not just during the examination, but in every production environment you will ever support. I look forward to our next session. Welcome back. In this chapter, we will master the essential functions and logical operators required to build robust and reactive logic within the Appian platform. If you want to pass the ACD101 exam, you must become comfortable with Appian's functional expression language. This chapter is your direct path to mastering the core utilities that power almost every interface and process model you will ever build. By understanding how to manipulate data, handle null values, and apply logic over arrays, you will significantly reduce development time and avoid common runtime errors. We will move past simple syntax and delve into the functional paradigms that make Appian logic predictable and modular. Whether you are validating a user interface or calculating values in a process model, the techniques discussed here form the bedrock of a professional associate developer's skill set. The foundation of any significant logical operation in Appian begins with the if function, which serves as our primary branching tool. Unlike procedural languages that rely on long if-else blocks, Appian expressions treat conditionality as a functional evaluation where both the true and false branches must be syntactically valid and type consistent. It is crucial to remember that if always evaluates its branches in terms of data types, so ensuring that both the true and false results return a consistent type is mandatory to avoid execution errors. Pair this with the isNull function, which is your first line of defense when handling data that might be missing from a process variable or a record field. Relying on isNull allows you to provide sensible defaults or alternate paths when your data layer returns empty sets, preventing the dreaded null pointer exceptions that often plague complex integrations. Always prefer these built-on, null-safe functions over manual comparisons, as they are optimized for the platform's internal engine and handle various data types with greater reliability. When moving beyond individual values, we frequently encounter arrays, which require a functional approach to processing. The apply function is our workhorse here, allowing us to map a specific rule or function across every element in an array without writing explicit loops. This functional style is significantly cleaner and more efficient than trying to iterate through variables using manual indexes. When you combine apply with the filter function, you gain the ability to extract specific subsets of data based on dynamic criteria, which is a common requirement in record displays and data grids. For instance, if you receive a flat list of items, using a filter with a predicate rule allows you to narrow down the result set to only those items that meet your business requirements. By adopting these array manipulation patterns, you keep your expression rules concise, easier to read, and substantially easier to maintain as your project requirements evolve over time. Logical operators such as AND, OR, and NOT are the connective tissue that binds your conditions together into complex decision-making trees. While these might seem straightforward, their power lies in how they handle null inputs and their ability to short-circuit evaluation in certain contexts. When you chain multiple conditions, always consider the readability of your expression. Nesting too many logical operators can quickly become a technical debt challenge for whoever maintains the code next. Good practice dictates breaking these down into smaller, reusable rules or using local variables to hold the result of individual conditions before combining them. Keep your logical expressions flat whenever possible, as this makes testing vastly simpler and debugging far more intuitive. If you find yourself needing to check multiple states, prioritize these built-in operators as they are designed to perform performant logical comparisons directly within the evaluation engine. Reflect on these functional patterns as you move forward. See you in the next lecture. Hello. Let's discuss how we bridge the gap between static user interfaces and live data by mastering the art of querying within expressions. This chapter focuses on the mechanics of retrieving precise datasets to fuel your application logic. In Appian, expressions are not merely for static calculations or string manipulation, they are the primary mechanism for dynamic data retrieval within the SAIL framework. When we talk about querying data with expressions, we are essentially moving away from reliance on process variables and shifting toward real-time data access. The two functions that dominate this landscape are a query record type and a query entity. While they share a similar purpose, they serve different layers of the Appian data architecture. Understanding when to use one over the other is a pillar of building performant interfaces. A query is essentially a structured map of parameters that includes filters, sorting, and paging information. By defining these parameters programmatically, you ensure that your components only retrieve the specific subset of data required, which is essential for maintaining a responsive user experience. Let us start with a query record type, which, as the name suggests, interacts directly with your defined record types. This function is typically the modern preferred choice when working with synced data or the data fabric. To construct this query, you provide the record type parameter along with a query object built using a query. Within that query, you define the paging info, which dictates how many items you receive and at what offset, and the filter, which allows you to narrow down results based on specific field values. Imagine you have a drop-down component that needs to show only active employees from a specific department. You would build a filter using a query filter, specifying the field as the department identifier and the operator as an equality check. This keeps the data load lean, as the database performs the heavy lifting of filtering before any records hit your interface. On the other hand, a query entity provides a more direct path to data sources, traditionally through data stores, though its usage has evolved alongside the data fabric. You must reference a specific constant that points to your data store entity. The structure remains remarkably consistent with the record-based approach, utilizing a query to package your requests. The beauty of this approach lies in the projection parameter, which allows you to specify exactly which fields you need to fetch. If you're populating a grid that only shows customer names and contact numbers, there is no reason to pull the full row object, including long memo fields or technical metadata. By project only the relevant fields, you reduce the memory footprint of your expression and effectively decrease the response time of your interface components. Efficiency in these expressions is not a luxury, but a requirement for a high-quality user experience. When building dynamic components like grids or charts, you're often dealing with asynchronous data loading. If you construct an inefficient query, you risk locking up the UI thread while the system parses through unnecessary records. Always remember that the paging info is mandatory for most query functions to ensure safety and performance. You should define your batch size based on the specific usage of the data. Use a small batch size for drop-down choices where the user only needs a few options, and adjust it for larger data displays where the user intends to scroll through lists. Never assume that the platform will optimize a poorly written query on your behalf. Sorting also plays a critical role in how the end user interacts with your application. A query without explicit sorting is non-deterministic, meaning the order of results might surprise you or change unexpectedly. By utilizing a sort info, you provide stability to your data displays. If you are retrieving a list of recent orders, sorting by the date field in descending order ensures the most relevant information appears first. This is particularly vital in UI components where a user might be searching for their last transaction. Combining filters, sorting, and paging into a single query constant or rule keeps your expression code clean and maintainable. This modular design allows you to reference the same data fetching logic in multiple locations, such as a process model and a UI interface, without duplicating the underlying effort. Think of these queries as the specialized interfaces between your business logic and the underlying storage layer. By formalizing these data requests into expression rules, you create a layer of abstraction that makes your application easier to debug and test. When you see a data display behaving oddly, you can inspect the expression rule that powers it, rather than hunting through the interface configuration itself. This separation of concerns is a core tenet of professional Appian development. It enables you to quickly swap or update data sources without tearing apart your interface design. As you grow more comfortable with these functions, you will find that almost all dynamic data displays rely on this consistent query structure. I will see you in the next lecture. Welcome back. We are now turning our attention to the design of reusable expression rules within the Appian environment. This chapter focuses on abstracting logic into modular units to ensure consistency and maintainability across your applications. In any non-trivial software system, the tendency for logic to duplicate itself is a constant gravitational force that leads to technical debt. If you find yourself writing the same expression, such as a complex calculation for a currency conversion or a specific user permission check, in multiple interface files, you have already created a maintenance burden. By creating standalone expression rule objects, you effectively move this logic into a single, addressable location. This is not merely an exercise in tidiness, it is a fundamental architectural decision that dictates the long-term health of your project. When you define an expression as a discrete object, you gain the ability to verify, test, and update that logic independently of the context in which it is consumed. This encapsulation is the bedrock of modular design in the Appian platform. Defining inputs for your expression rules is the first step toward creating truly fungible components. Just like a well-designed function in a traditional programming language, your rule should have a clear, typed parameter list that defines what it expects to receive. When you define an input, you are establishing a contract with the rest of the application, declaring precisely what data is required for the logic to execute correctly. Avoid the temptation to hard-code variable references directly inside the rule body, if those values might change based on the caller's context. By utilizing parameters, you ensure that the rule remains a pure, predictable component that behaves deterministically based on its inputs. This disciplined approach to parameterization makes your rules significantly easier to debug when something eventually goes wrong. Once your inputs are defined, the body of the rule acts as the execution engine for your data transformation or logic evaluation. Writing the body requires a clear understanding of the expression language, ensuring that your operations are both efficient and easy to read for any other developer who inherits your code. Keep the body focused. If an expression rule begins to do too many things, it is almost certainly time to decompose it into smaller, more granular rules. Remember that readability is a primary concern in software delivery, as code is read far more often than it is written. Use constants for static values to avoid magic numbers or strings, and leverage built-in functions to perform common transformations instead of reinventing the wheel. The goal here is to create an implementation that is so straightforward that its intent is immediately obvious to any peer. One of the most powerful features of these objects is the ability to invoke them throughout your application using the rule prefix. This convention allows the Appian engine to resolve the dependency at runtime, effectively creating a pointer to your shared logic layer. Because every reference points back to the original object, a single change to the core rule body ripples across every interface or process that utilizes it. This centralization eliminates the risk of logic discrepancies that occur when you have multiple, slightly different variations of the same business rules scattered throughout your workspace. It also transforms your development process into an exercise of composition rather than duplication. Instead of rebuilding common features, you simply look up the appropriate rule and pass the necessary arguments, which significantly speeds up the implementation phase. The benefits of this abstraction become most apparent when you consider the maintenance lifecycle of an enterprise application. Business requirements are, by their nature, rarely static, and you will inevitably need to adjust your logic to accommodate new policies or regulatory changes. If your logic is centralized, you can make a single modification, observe the impact in the rule testing interface, and deploy the update with confidence. This reduces the regression surface area significantly because you are not hunting down every instance of a logic snippet hidden in 50 different interfaces. By designing for reusability from the start, you treat your expression rules as first-class citizens in your application's architecture rather than as secondary utility files. This is the difference between an application that grows rigid over time and one that remains flexible in the face of inevitable change. See you in the next lecture. Welcome back, as we turn our focus to the vital practice of ensuring our expression rules behave exactly as we expect them to under various conditions. In this session, we will explore the mechanics of testing and debugging within the Appian expression editor. When you open an expression rule, you will notice the test inputs pane located below the expression editor. This interface is not merely a scratchpad. It is the primary environment for executing your code against representative data. By defining specific values for each rule input, you can simulate user behavior and system data without needing to run a full process model. The ability to save these configurations as test cases is a powerful feature that allows you to establish a baseline for correctness. Whenever you modify the logic, you can simply click your saved test cases to verify that your changes have not introduced regressions. If you do not adopt this habit, you are essentially flying blind, hoping that your changes haven't broken existing dependencies that rely on your rule. Testing should never be an afterthought, especially when your rules are responsible for complex calculations or data transformations. Consider the scenario where you are processing an array of records to calculate a total price. You must explicitly test for empty lists, null record values, and extreme numerical inputs to see how the expression evaluates them. If an expression encounters an unexpected null value, it might return a null result or, worse, throw a runtime error that halts the user interface. By setting up test cases for these edge cases within the rule editor, you proactively catch these issues before they manifest in a live production environment. You are essentially building a safety net that gives you the confidence to refactor and optimize your code over the life cycle of the application. When an expression fails, Appian provides feedback that helps you pinpoint the origin of the logic error. You should pay close attention to the error messages displayed in the evaluation pane, as they often identify the specific function or operator that failed to process the input correctly. Sometimes the message will reference a mismatched data type, such as attempting to perform arithmetic on a text string or passing a single item where an array is expected. Interpreting these messages is a skill that evolves with experience. But looking for the specific line or function highlighted in the stack trace is always the right place to start. A stack trace essentially tells you the history of calls that led to the fault, providing a breadcrumb trail back to the root cause of the evaluation failure. Dealing with complex expressions requires a methodical approach to debugging rather than guesswork. If you have a deeply nested rule, start by breaking the logic apart or using local variables to store intermediate results so you can inspect them individually. You can return these intermediate values directly to the tester to see if the error is occurring at an early transformation step or during the final output generation. This strategy of isolating variables is identical to the techniques we use in other programming environments to keep logic pure and inspectable. By keeping your rules granular and ensuring they only handle one responsibility, you naturally make them easier to test and debug, which is a hallmark of maintainable code. See you in the next lecture. Welcome to a discussion on the decision object, a powerful tool for encapsulating business logic outside of your standard expressions. In this module, we will explore how to model complex rules using logic tables to keep your applications clean and maintainable. The decision object in Appian functions as a centralized engine for evaluating business rules, providing a clear visual interface that replaces what would otherwise be a dense, unmanageable wall of nested if statements. When you find yourself writing complex conditional logic, such as determining an insurance premium based on multiple variables, placing this logic inside a decision object is almost always the superior architectural choice. This approach decouples the decision-making process from the surrounding code, offering a configuration-based alternative that business stakeholders can read and understand without needing to parse through expression language syntax. By separating the rule from the logic, the developer gains a distinct advantage in maintainability and testing, as changes to the business policy can often be addressed entirely within the decision table without modifying the core process or interface code. At the heart of the decision object is the concept of hit policies, which dictate how the engine evaluates rows and returns results when multiple rules might match the input criteria. If you select the unique hit policy, you are asserting that only one row can possibly match the input parameters. If more than one matches, the object will return an error, which serves as a robust mechanism for enforcing strict data integrity rules. The first hit policy, by contrast, takes the output of the first row that evaluates to true and ignores all subsequent rows, providing an intuitive top-down approach for cascading logic. If you require more flexibility, the any hit policy allows for multiple matches to return values, and you must define how those multiple results are aggregated, such as returning the sum, minimum, maximum, or a list of all matching outputs. Choosing the correct hit policy early in the design phase is crucial because it fundamentally alters how your downstream process models or interfaces perceive the returned data. When deciding between a decision object and a nested if expression, you should consider the cognitive load placed on the developer and the accessibility of the rule for non-technical users. A nested if expression is essentially a hidden, hard-coded constraint, accessible only within the specific function where it is defined, which makes it difficult to audit or adjust quickly as business requirements evolve. In contrast, the decision object is a first-class citizen in Appian, treated as a reusable component that can be called from multiple processes and interfaces, ensuring that the business logic remains dry and consistent across the entire application. The visual matrix format provided by the decision object is particularly effective for pricing tables, approval routing paths, or complex classification tasks, where the input variables determine a discrete output category. While an if expression is perfectly fine for simple binary toggles or straightforward truth checks, moving toward a decision object scales far better as your application grows in complexity and the number of conditional branches increases. The visual configuration of these logic tables allows you to map various input attributes, such as region, customer tier, or transaction size, against multiple columns to dictate the final output value. As you construct these tables, you will notice that the interface allows for explicit definitions of ranges, null checks, and default outputs, reducing the risk of unexpected results during runtime. Developers should view these tables not just as static containers, but as active components of the application's configuration layer, which can be versioned and deployed independently of the processes that call them. If your logic requires significant changes in the future, updating a decision object ensures that those changes propagate across all call sites, eliminating the need to search through hundreds of lines of obscure code. This methodology aligns with the principles of clean design, where we minimize entropy by keeping specific business policies in predictable, easily accessible locations rather than embedding them deep within the procedural flow of the application. I will see you in the next lecture. Hello, and welcome back to our deep dive into the practical aspects of Appian development. Today, we are shifting our focus to managing static data and environmental configuration through constants. In any reasonably complex software system, hard-coding values directly into your logic is a practice that breeds maintenance nightmares. If you find yourself typing a specific folder ID or a base web address directly into an interface or a process model, you are creating a brittle dependency that will break the moment you move that object between environments. Appian provides the cons domain specifically to address this concern by decoupling the value from the implementation logic. A constant acts as a placeholder or a reference for a fixed value, such as a document object, a group, or an integer representing a maximum threshold. By relying on these references, you ensure that your code remains generic and focused on business rules rather than specific infrastructure identifiers. This abstraction is a fundamental pillar of writing clean, maintainable, and professionally structured applications. The most compelling reason to utilize constants is to facilitate environment-independent deployments. When you migrate an application from a development environment to a test or production environment, the underlying system IDs for things like user groups, folders, or document templates will almost certainly change. If those values were hard-coded as literal strings or numbers in your expression rules, you would be forced to manually edit every single object after the migration, which is an error-prone and inefficient workflow. Instead, you define a constant in your package, and upon deployment, you merely update the value of that constant within the target environment's admin console to point to the correct local object. This means your application logic remains untouched, as the expression engine resolves the reference dynamically at runtime based on the object provided in the new environment. When it comes to organizing your constants, naming conventions are far more than just a matter of subjective preference. You should adopt a descriptive, consistent naming strategy, perhaps using a prefix that identifies the module or functional area to which the constant belongs. Furthermore, think critically about the scope and organization of your objects within the Appian Designer. Placing constants in a dedicated folder structure, mirroring your functional design, allows you to quickly locate and audit these values during troubleshooting sessions. Avoid the common pitfall of creating dozens of disparate, unorganized constants that serve overlapping purposes. Instead, consolidate your configuration values and treat them as a centralized configuration layer for your entire application architecture. It is also important to note that constants are not merely for holding static strings or integers. They are frequently used for storing references to system objects, such as specific user groups used for task routing, or particular document folders where generated reports should reside. By referencing a constant in your process models, you avoid the need to open and modify nodes after migrating software. When you need to retrieve the value, you simply call the constant using the cons domain followed by its name, returning the object or value assigned to it. This approach keeps your process diagrams clean and readable, as the nodes describe the intent of the action rather than the specific, low-level identifier of the storage location. Always strive for a design where the constant is the single source of truth for all environment-specific variations. If a value changes across your different deployment targets, it should exist as a constant. If a value remains identical across every installation and is fundamental to the logic, you might consider if an expression rule or a configuration object is more appropriate, but usually, constants provide the safest middle ground. Think of them as the configuration variables of your application, and treat them with the same care you would apply to your database schema or your API integration endpoints. Mastering this simple yet powerful feature is a hallmark of a developer who understands that software is not just written, but deployed and maintained over its entire lifecycle. I look forward to seeing you in the upcoming discussion. Welcome to the chapter on logic performance and optimization, where we focus on writing efficient code for the Appian expression engine. We will explore how to manage function costs and optimize memory usage to ensure your applications remain performant under scale. When we talk about the Appian expression engine, it is crucial to recognize that it is a functional, lazy evaluating architecture. Every function call carries a computational cost that, while often negligible in isolation, can become significant when amplified within loops or large datasets. Developers frequently make the mistake of performing expensive operations, like querying the database or manipulating complex structures inside a for-each loop. A query executed within a loop is an order of magnitude more expensive than a single query returning a larger set that is later filtered in memory. By shifting these operations outside of iterative constructs, you reduce the round-trip overhead to the data layer, which is typically the primary bottleneck in any enterprise application. Consider the way we process lists and data structures as part of our core design responsibility. Using functions like a flatten can be incredibly powerful for normalizing data, but it comes with a memory cost because it forces the expression engine to materialize the entire nested structure into a single linear list. If you are dealing with thousands of items, flattening can lead to high memory consumption, potentially slowing down the entire interface or process model. Instead of flattening unnecessarily, see if you can operate on the nested structure using higher order functions like apply or rewrite that handle iterations more gracefully. Always keep an eye on the scope of your variables, as holding large data sets in local variables within a complex interface can drastically increase the memory footprint of your user session. Another common performance trap involves the misuse of querying functions inside sale expressions. Because sale is rendered every time a user interacts with a component, any query included in an interface component is re-executed if it is part of an evaluating expression. To optimize this, leverage local variables with the aLocalVariables function to cache query results rather than placing the aQueryEntity function directly inside a component's parameter. By defining your data in a top-level local variable, you ensure the data is fetched only once during the initial load or refresh cycle. This simple pattern effectively shields your backend from redundant requests and makes the user experience perceptibly faster. When working with complex business rules, we often rely on custom expression rules to perform validation or data transformation. The temptation is to pass entire records into these rules, which can inadvertently cause the engine to pass and evaluate large data structures back and forth. You should strive to pass only the specific primitive fields required for the logic inside the rule rather than the entire data object. This reduces the serialization and deserialization overhead that occurs when passing data between rules. Additionally, ensure that your logic avoids recursive calling patterns unless strictly necessary, as uncontrolled recursion can hit depth limits and consume excessive CPU cycles, leading to timeouts in your process models. Think of the expression engine as a specialized compiler that performs best when it has the smallest possible working set of data. When you design an expression, you are essentially writing a set of instructions for the engine to execute as quickly as possible. If you provide it with an inefficient algorithm like an O(n) squared operation, you are effectively asking the engine to do unnecessary work for every single element in your list. Always profile your expressions and favor built-in functions over complex, nested logic whenever possible. The built-in library is optimized for these low-level tasks, and it will almost always outperform manual, custom-coded workarounds in terms of raw execution speed. Performance is a consequence of deliberate choices made during the early stages of development. By adhering to these principles of data minimization and efficient path planning, your applications will scale effectively as your user base and data volume grow. Enjoy the process of refining your logic. Welcome back to our final session where we consolidate everything you have learned throughout this course. We will refine your understanding of the core Appian pillars and ensure your readiness for the certification exam. To reach the level of proficiency required for the ACD101 exam, you must view Appian as a unified ecosystem rather than a collection of disparate tools. We have built applications starting from data structures, moving through process orchestration, and finalizing with the user interfaces that surface this logic. When reviewing your knowledge of data, consider how CDTs and record types act as the backbone for every flow. Your ability to distinguish between when to use a data store and when to leverage the modern data fabric is critical. Remember that the Appian way prioritizes low-code patterns that minimize technical debt. As you approach the exam, ensure you can map each requirement to the most efficient object type, avoiding unnecessary complexity in your architecture. Transitioning into application deployment, the mechanics of moving code between environments are as important as the code itself. You should be comfortable with the concept of creating packages and exporting them, as this is the standard mechanism for releases. Think of your application as a living entity that requires version control via patches for incremental updates and hotfixes. Security remains a non-negotiable pillar throughout these movements. Review the specific permissions associated with the administrator, editor, and viewer roles, and be certain you understand how object-level security overrides or complements group-based access. Always perform a final checklist review of your environment settings, including constants and external system connections, to ensure that the release candidate is fully portable. Process orchestration and logic performance are often the areas where subtle certification questions are hidden. Revisit your understanding of activity chaining and process variables, specifically how they impact user experience and load on the server. If your process model hits a bottleneck, it is usually because of inefficient wait states or poorly configured gateway logic. Apply the same rigorous standard to your interface design by focusing on SAIL performance best practices. Ensure you are using local variables correctly to optimize content rendering, rather than forcing repeated rule evaluations. Efficient expression logic is the hallmark of a developer who respects the underlying platform architecture and its resource consumption capabilities. On the day of the exam, time management is your most valuable asset. Do not get bogged down by complex wording. Look for the keywords that indicate the preferred Appian solution pattern. The exam tests not just your academic knowledge of functions, but your practical judgment in choosing the right tool for the job. Read each scenario carefully, identifying the intent behind the requirements before jumping to the answer choices. Keep your focus on the core architectural principles we have discussed throughout our time together. By maintaining a clear perspective on how data, process, and interface components interact, you will navigate even the most challenging questions with confidence. I wish you the very best of luck on your certification journey. See you in your next milestone.